Okay, good evening, my dear students. Welcome to Gradeup. So, I welcome you all to this live session on loss of radiation. Yesterday, we have discussed some of the basic concepts of radiation from the heat transfer subject. And you might be knowing about the different concepts, the different terminologies which we have discussed in the yesterday's lecture. And we have started the Stefan-Boltzmann's equation also. In the yesterday's lecture, we have discussed about what is Stefan-Boltzmann equation and what is the physical significance of different bodies like black body, grey body, white body. Okay, so let us wait for a while so that you guys can join me to this live session on loss of radiation. Today we'll be discussing about the different loss of radiation, and dedicatedly we are having this session for the GATE 2021 aspirants so that they can brush up their technical aspect, they can improve their technical knowledge, and they can have a confidence on this subject. Okay, because heat transfer is a very easy subject to understand. We are having a very good concepts behind this. Clear? So very good evening, Mohammed. So welcome you to this live session. So how are your preparations going on? Yes, tell me how many of you are alive. Please respond so that I will be getting to know that you are live with me and you are able to understand which I am delivering. Okay, very good evening, Monisha. Clear. So how was your yesterday's session? I hope so you understood the basic concepts of radiation. Okay, so radiation, if I talk about the radiation topic, you must have studied about the emissive power yesterday's. If I talk about the yesterday's lecture, you might have studied about the total hemispherical emissive power, the emissivity, monochromatic emissivity, different terminologies you might have come across if you had see the yesterday's lecture. This is basically the continuation of this yesterday's lecture. We end up with the Stefan-Boltzmann equation. So let me conclude, start the session. So this is about my profile. I've done my master's in thermal engineering. Clear? So and this is my area of expertise where I have completed my where I have the subjects masters in these of the subjects. So without wasting the time, let us start our session. So any doubt in the yesterday's session? If you are having any doubt, do let me know. Clear? So radiation topic. Fine. So if I talk about this, the second law of thermal radiation is Kirchhoff law of radiation. Any idea from this topic, Kirchhoff law of radiation? Very good evening, Afzal. Yes, Kirchhoff law of radiation. Any idea what is Kirchhoff law of radiation? The Kirchhoff, what is it? This statement of this Kirchhoff law of radiation. If I say Kirchhoff law of radiation, this basically tells us about if a body is at thermal equilibrium, if a body is at thermal equilibrium, then the absorptivity of that body will be equal to the emissivity of that body at that temperature. Yes, you can brush up your concept, Praveen. Like if you are going for 2020, if you are having any doubt in the laws of radiation, you can definitely attend this session and you can clarify your doubts, the doubts which you are having for this topic. So if I talk about this Kirchhoff law of radiation, Kirchhoff law of radiation states that if a body is in thermal equilibrium with the surrounding, then the absorptivity of that body will be equal to the emissivity of that body. So, so from this equation, I can directly say a good absorber is always a good emitter. Is always a good emitter. Because okay, you are having the doubt in radiation shield. Tomorrow we'll be discussing on Monday, not tomorrow, on Monday we'll be discussing about the radiation network where we'll be talking about the radiation shield also. Okay, so Sandhya, clear? Afzal, we'll be again resuming the videos of ISRO. We'll see what are the schedules we are having, where we'll be giving you the latest plan of ISRO so that you can have a very good preparations. Praveen, it is not yet over for GATE 2020. It is not yet over. We'll be giving you some of the lectures so that you can improvise your concept on the subjects. Clear? So do let me know what are the subjects you want to have the revision, so that we will be having an idea, and we'll be telling you about the subjects which you need to get a brush up for the GATE 2020. Now this session, this series is basically started for all the aspirants who are giving for GATE 2021, so that we can start from the basic concept. If you are going for the GATE 2020, this is not the right time, because this is the basic concept. At this stage, you should be applying that concept. You need to solve as many problems as you can if you are going for GATE 2020. Clear? So coming back to this, Kirchhoff law of radiation, if a body is a thermal equilibrium with the surrounding, the absorptivity will be equal to the emissivity of that body. So by this statement, I can also say that a good absorber is always a good emitter. So that is why black body, you remember the yesterday's lecture, black body, I have told you it is a perfect absorber, and also it is an ideal emitter. So by this law of radiation, we can justify that statement that a perfect absorber is also a very good emitter. Clear? So that is why this is a very important concept. If I talk about the black body point of view, a good absorber is always a good emitter. So by using this equation, you can will be solving some problems in the third lecture, where we'll be discussing about the physical significance of this this equation, where we'll be applying in the radiosity and irradiation topic. Clear? That is, we'll be covering under radiation network. So before that, you should know what are the different laws of radiation. After that, we'll be talking about the different radiation network. Clear? So any doubt in this? Any doubt in this Kirchhoff law of radiation? It's very easy to understand. If a body is at thermal equilibrium, then with the surrounding, then the absorptivity will be equal to the emissivity of that body. Clear? Next, Planck's law of thermal radiation. Now it's a very interesting topic, Planck's law of thermal radiation. What happened, Mohammed? You're not able to see the previous one. It's written in the black pen only. I hope so you are able to see this, which I have written over here. Let me check one second. Okay. I hope so you are able to see this. Next, Planck's law of thermal radiation. Now this is a very important. It's a very important law of thermal radiation. Now Planck suggested that the monochromatic emissive power of a black body is basically a function of wavelength and absolute temperature. Planck basically, he had some experiments with the different bodies, and what he found that the monochromatic emissivity of a black body is a function of wavelength as well as the absolute temperature. Clear? So by using this empirical formula, he derived this equation. He came this by using an empirical formula. No need to remember this formula. Never ever you will be getting this question from this formula, but you need to understand the concept behind this. The concept is the monochromatic emissivity of a black body is a function of wavelength and absolute temperature. Fine. So by experimentation, he found out an empirical formula where there are some parameters, where C is speed of light, lambda is wavelength in micrometer, H is Boltzmann constant, which is equal to 1.3 into 10 to the power minus 23 joule per Kelvin. Any other? T is absolute temperature in Kelvin. Fine. So these are the different parameters which you should know. Planck's, he derived from an empirical formula that the monochromatic emissive power of a black body is a function of wavelength and absolute temperature. He found out empirical formula. where there are different terms which you need to understand. C is speed of light, lambda is wavelength in micrometer, T is absolute temperature in Kelvin, and H is Boltzmann constant, which is 1.3 into 10 to the power minus 23 joule per Kelvin. Now, when you plot a graph between the monochromatic emissivity of a black body EB lambda and lambda, he found out that the curve was something like this. Yesterday also when we were studying about monochromatic emissivity, I told you about this curve where the integration of monochromatic emissivity for whole wavelength tells you about the total emissive power. Clear? Yesterday we have studied this. The total emissive power is basically the integration of 0 to infinity, the monochromatic emissivity into d lambda. This is also applicable for the black body. Now, this is the pattern which we are getting by using this equation. He plotted different curves and he got the curve something like this, which is your monochromatic emissivity with wavelength, monochromatic emissivity with the wavelength. He found out that we are having a curve something like this. Clear? We are having it is initially increasing, then it is decreasing. K is it's not H, it's K. Boltzmann constant is K. H is, what is H? It's Planck's constant. K is Boltzmann constant and H is Planck's constant. Fine, just rectify this. Now, no need to go into deep this equation, just only you need to understand this curve because the questions are basically repeated and the concept is basically kept in this curve only. So, Planck's, he gave equation and from this equation he plotted a graph between monochromatic emissivity of a black body with the wavelength, and he found out that at some wavelength, take it as that wavelength corresponding is sigma your lambda m, corresponding to that wavelength we are getting a maximum black body emission, Emax. Clear? We are having n number of wavelengths. At some particular wavelength we are having some the emissive power to be maximum at some point. Take this point as A. So at point A, what we are having, corresponding to this wavelength we are having a maximum emissive power. Clear? So in addition to this, you might be knowing about vanes. Displacement law. In addition to this, the vanes, he gave the statement that the absolute temperature is inversely proportional to the maximum wavelength. According to the Vane's displacement law, he stated that the maximum wavelength corresponding to the emissive power, the maximum emissive power, which is this one. What is lambda m? Lambda m is basically that wavelength where we are having the maximum emissive power. So if I say by using this Vane's displacement law, he said that the lambda corresponding to the maximum emissive power is inversely proportional to the temperature. That means what I can infer from this, I can infer that if we are having shorter wavelength, that means the temperature will be high or low. If I am saying we are having a shorter wavelength, then in that case what will be the temperature? It will be high or low. If you see from this equation, if I say we are dealing with shorter wavelength, then the temperature will be high or low. Quickly tell me. Will it be high or low? If you are dealing with shorter wavelength, it will be high temperature, because you have seen from this equation, very good Anju, you have seen from this equation, your maximum wavelength corresponding to the maximum emissive power will be inversely proportional to the absolute temperature. So what does that mean? That means if we are dealing with high temperature, that means we will be having shorter wavelength. Let us take one example, a basic example. You might have seen in the cars, like initially your sun rays is coming inside the car, and after reflection, fine, or after emission, what is happening? Some of the wavelength is being reflected back. So can you tell me which of the wavelength will be having more, which of the wavelength will be the more magnitude, A or B? There are two radiations. One is incident radiation coming from the sunlight, which is radiation A, fine, or emission A. and we are having a reflection from the inside of the seats which we are having inside the car. So can you tell me which of the wavelength will be higher, A or B? A. Clear? Why A? Because initially the temperature is high. We are having high temperature. Clear? It is coming inside the car. After reflection, what is happening? Its temperature is being dropped. If the temperature is dropped, so what will happen? Your wavelength will increase. So that is why what happens due to this is the explanation of the greenhouse effect. Clear? So what is happening? If you are having a car, inside that car, if all the windows are closed, after some time what will happen? You will feel the temperature inside the car is increasing. Why it is increasing? Because the wavelength, the radiation or emissions having shorter wavelength it can easily penetrate through the glasses and it can go inside the car. But after reflection, what is happening? It is losing, and the wavelength, the magnitude of the wavelength is increasing. So what will happen? It won't be it won't be coming out from the car. So your temperature inside the car will increase. So that is a reason of greenhouse effect. That is the reason of greenhouse effect. That is the main reason of greenhouse effect. Clear? Understood what the application of this? Now try to let us understand what is this Wien's displacement law, what is the graph which we are trying to understand from this. Now we have drawn three curves. Clear? We have drawn three curves. Take it this curve as curve A, this is curve B, and this is curve C. Clear? I have drawn three curves, and all the three curves are drawn for different temperature. For curve A, the temperature is 2000 Kelvin. For curve B, the temperature is 1000 Kelvin, and for curve C, it is 500 Kelvin. So, can you tell me what is the pattern which you are seeing? Can you tell me what is the sequence of the maximum wavelength? What is the sequence of maximum? Which of the radiation will be having the maximum wavelength? Delta M. Quickly tell me whether it will be for A, B or C. Quickly tell me what will be the pattern of lambda M, for which will be having the highest? It is A, B or C, or which will be the lowest? A. Clear? If I see in the increasing order, if you write in the increasing order, so your lambda M for radiation C will be greater than lambda for B and lambda for A. Clear? Also, what we have understood, your temperature for A is greater than temperature of B is greater than temperature of C. So this is the same statement which the Wien's gave us, that if the absolute temperature is increasing, so what will happen? Your curve, the top of the peak of the curve will be shifting towards the left. That's the main inference of Planck's and Wien's displacement law. Clear? That is the most important concept. If you are increasing the temperature, what will happen? If you are increasing the temperature, what will happen? The curve will shift towards the left. That means the peak point of the curve will be shifting towards the left. What is this peak point? This peak point is basically corresponding to the maximum monochromatic emissive power of a black body. Understood? What is the physical significance of this curve? If you are not able to understand, do let me know, because this is the most important concept from Wien's displacement and Planck's law. Any doubt in this? If you are having any doubt, do let me know, because if you are able to understand this curve, then you can easily you will be easily solve any problem coming from this Wien's displacement law. Clear? And Wien's after doing calculation, he found out that the maximum wavelength into the absolute temperature is equal to approximately 2898 micrometer Kelvin. After getting by a permutation combination, by applying this formula, he found out that the lambda M into T is approximately equal to 2898 micrometer into K. Clear? So if you are having 2-3 parameters given, you can easily get the parameter third. we can take one example so that you will be able to understand. Example is something like this. We are having lambda m A is equal to 100 micrometer. Temperature A is 1000 Kelvin. Temperature B is 200 Kelvin. So can you tell me what will be the maximum temperature for wavelength B? Quickly respond to this. We are taking an example from Waves Displacement Law. There are two wavelengths. The maximum wavelength for A is 100 micrometer. For TA, the corresponding temperature is 1000 Kelvin. Temperature for B is 200 Kelvin. So what will be the maximum wavelength for body B or wavelength B? Can you tell me what should be the answer? Because these are some 1 marks problem which they are asking from this basic concept. Clear? And every year you can expect one problem from this Waves Displacement Law. Clear? So try to tell me quickly what should be the answer. Very good, Anju. Okay. Okay, so we got two variation of answer. I'm getting 20 also and 500 micrometer. Let us check. It's a direct formula. Now, you no need to take this value because you can directly write delta MA into TA is equal to delta MB into TB. Clear? Now, 3 parameters is given. Directly you can put the value. This is 100 into 1000 is equal to 200 into TB. Just cancel out some of the terms. They can directly say TB is equal to 500. Oh, sorry, not TB. This should be lambda M. Lambda MB. So lambda MB is basically 500 micrometer. Understood? The physical significance. I have shown you the example also how the question is coming from this Waves Displacement Law. So by using this example, you can directly get the value of the maximum wavelength where we are getting the maximum emissive power. Clear? So this is that wavelength where we are getting the maximum emissive power. That means if you take this example, for wavelength A, we are having n number of wavelengths, but at some particular wavelength only we are getting the maximum emissive power, which is lambda MA. For particular B, we are getting the maximum at lambda B, lambda MB, and this is for lambda MC. Clear? So if your temperature is increasing, what will happen? Your curve will shift towards the right. That means your maximum wavelength corresponding to that maximum emissive power will be decreasing. So this is the concept behind the Waves Displacement Law. Clear? If this is clear, shall we move to the next law of radiation? Okay. Next is Lambert Cosine Law. Very important. Many of the students are having doubt in this Lambert Cosine Law. I've taken many sessions and every time the students are confused with this Lambert Cosine Law. What is this Lambert Cosine Law? And there are some parameters being introduced. So before going into this Lambert cosine, I'll be telling you the two parameters which is being introduced for understanding this topic. The first parameter is solid angle. Solid angle. So can you tell me what is this solid angle? What is a solid angle? Because this is very important. For understanding Lambert Cosine Law, there are two parameters. One is solid angle and second is intensity of radiation. If you are able to understand these two concepts, then you can understand this Lambert Cosine Law. Now, can you tell me what is solid angle? Or what is the difference between a solid angle and a normal linear angle? If I say there are two lines and in between this line we are having the angle, this is theta. Clear? But what do you mean by solid angle? Very good. Rutik and Akhilesh, very good. Angle of cone. So basically, solid angle is it is defined for a three-dimensional plane or three-dimensional body. Now, normal angle, which I've told you in the intersection line, that is defined for a two-dimensional space. But if you are talking about the angle for the three-dimensional space, that is called solid angle. So for understanding, I have given you this. I have given you a diagram. Now we are having a hemisphere and this surface. Take this surface. If I want to know what is the angle subtended by this surface, this is basically the solid angle. This one is the solid angle. Clear? Where the solid angle is basically, the solid angle is normally denoted as omega. So omega is equal to surface area upon radius square. Surface area upon radius square. Clear? So this is the formula of solid angle. And what is solid angle? Is basically the angle subtended by that plane or by that surface. Fine. And if you take the projection of that to a single point at the center of the hemisphere, so that angle which is being suspended, like when you switch on a torch light. For example, if you are having a torch, fine, we are having a torch and we are switching off this on this light. So what will happen? It will scatter like this. So the solid angle will be, if you say the front portion, this angle is basically the solid angle. Clear? It's in the three-dimensional view. Clear? Fine. Now, what is the unit of this solid angle? Can you tell me what is the unit of solid angle? What is the unit of solid angle? A normal two-dimensional, the unit of two-dimensional angle is radian. Clear? So what is the unit of solid angle? Very good. MATLAB Productions, Akhilesh, very good. Obviously, the unit of solid angle is steradians, normally denoted as SR. Steradians is normally denoted as SR. Very good. Now, Sharmila, it is not radian. Radian is defined for a two-dimensional body. Now, this is for a three-dimensional body. So, for three-dimensional body, we won't be using a radian. Instead of radian, we'll be using the new unit, which is called steradian. Okay, Sharmila? Manoj, correct? Rutik, unitless maybe? No, it will be having, definitely will be having unit. Clear? Like, if you say we are having two lines, which intersection having 30 degree, fine. So degree is also a unit, fine. If you convert into radian, then we'll be having some value. Clear? So this is about the solid angle. The next important parameter which you should know is intensity of radiation. Intensity of radiation. Now, what is intensity of radiation? Can you tell me? Normally denoted as capital I. What is intensity of radiation? If you want to define what is intensity of radiation, intensity of radiation, I will writing the equation for you, then you will be able to understand. Intensity of radiation, basically, it is the total emissive power of a body, total emissive power of a body per unit. It is a total emissive power of a body in any direction per unit solid angle per unit area is known as intensity of radiation. I am repeating once again. What is intensity of radiation? Intensity of radiation is basically, it is the amount, or we can say the magnitude of emissive power per unit in any direction per unit solid angle per unit area. So if I want to write what is the unit of this I, it will be watt per meter square steradian. Watt per meter square steradian. Fine? Clear? So can you tell me what is the difference between intensity of radiation and monochromatic emissive power? Very important concept. What is the difference between E lambda and intensity of radiation? Quickly tell me, what's the difference between the two? Because if you are able to differentiate between these two terms, then I hope so you understood the difference between, you understood the basic concept of radiation. So quickly tell me, what is the basic difference between monochromatic emissive power and intensity of radiation? Which one is defined for which parameter? If you are able to know, if you are able to differentiate between these two terms, then I can relate that you have understood the basic concept of radiation. You have understood the previous lecture also, if you are able to judge difference between these two. Quickly tell me, what is the difference between the monochromatic emissive power and intensity of radiation? Anyone who can tell me? Rutik, Sharmila, Ajit, Jayesh, quickly tell me what emissive power is a quantitative measurement of entire body and it is used for particular area. Okay, very good. Anyone else? Monochromatic emissive power is for wavelength. Very good, Bhavesh. Very good. And what about intensity of radiation? Bhavesh? Look, let me take one example. From this example, I will be helping you out. There is one plate. Let us take one plate only. From this one plate, I will be telling you. Let us take one plate. We are having emission. Let us take this as the emission, and this is all for some particular wavelengths. Clear? Now, also we can define the emission in case of the direction also. Like this is for direction 1. Take it as I theta 1. This is your I theta 2. Clear? So, if you are defining the emissive power for particular direction, for a given direction, then that is defined for that parameter is known as intensity of radiation. But if you are defining the emissive power for particular wavelength, then that parameter will be known as monochromatic emissive power. This is the main difference between monochromatic emissive power and intensity of radiation, because many of times students are confused. Both are same, both are unidirectional, but what is the difference between the two? So the main difference is the monochromatic emissive power is defined for a particular wavelength and your intensity of radiation is defined for particular direction only. Clear? Understood? Fine. This is defined for a particular direction only, which is called a solid angle. What is I? I is defined the total emissive power for in a given direction per unit solid angle. Clear? This is the intensity of radiation. And what is emissive power? Emissive power is basically, it is the total emissive power defined for a particular wavelength. Clear? Understood the difference between the two? Now, coming to the Lambert Cosine Law. Lambert Cosine Law states that the intensity of radiation at any angle, normal to the surface is equal to the intensity of radiation which is normal to the surface. Let me write IN into cos of the theta, cos of the angle between the normal and the given direction. I have given you this diagram so that you can be able to understand this. This is the intensity of radiation which is perpendicular to the surface or normal to the surface, which is IN, and this is intensity at any angle theta. From this is basically the solid angle theta. This is your solid angle. We are basically having this. If you take this as projection, this will be your solid angle. So I have used a 2 dimensions so that you will be able to understand it clearly. Fine. So this is IN, I theta. So this will be I theta at any direction is equal to IN cos theta. So can you tell me in which direction we will be having the maximum intensity of radiation? If you are having a surface like this, so can you tell me in which direction we will be having the maximum intensity of radiation? Is it at along the surface or perpendicular to the surface, or at an angle 45 degree with the surface? Got my question? At what inclination you will be having the maximum intensity of radiation? In the normal direction. Very good. Exactly, from this equation also you can see, because cos theta, the range of cos theta is basically less than equal to 1. So you can directly say the maximum intensity of radiation is always normal to surface. It is always normal to surface. Clear? It is always normal to surface. Very good, Bhavesh. Clear? So this is your Lambert Cosine Law. Clear? Yesterday I told you about the black body, the definition of the black body. The black body was a very good absorber, and it is also a very good emitter also. You have seen from the Kirchhoff's law, like a good absorber is also a very good emitter. Fine. And also about the diffuse surface. Now this is a diffuse surface. What is diffuse surface? Diffuse surface basically means in all the direction you will be having the equal magnitude of the emissive power. Okay. If you say If you say this is the intensity of radiation, in all the direction will be having the same magnitude. This is called diffuse surface, and diffuse surface is basically the black body. This is basically, we are talking about the black body, because for the black body what is happening, we will be getting equal magnitude of intensity of radiation at each and every angle. Clear? So if I want to write what is the total black body emissive power in terms of intensity of radiation, can you tell me? If I say in all the direction we are having the same intensity of radiation I, so can you tell me what will be the equation of black body emissive power? Quickly. If in the all direction we are having the same intensity of radiation, this is a black body, so can you tell me what is the relation between your emissive power, the total emissive power of a black body with the intensity of radiation? It will be the total, because what is emissive power is basically this integration of I dW. It is basically, if you integrate the intensity of radiation with all the solid angle, that will be giving us the total emissive power. So I can write, because in all the direction we are having a same I, so this will be I into pi. So always remember, for a black body, your the relation between the black body and intensity of radiation is EB is equal to I into pi, because we are having, it is being defined for all the direction we are having the same magnitude, so we can integrate it. It will be pi times, because that will be pi, so pi times I. Clear? Understood? This is the black body emissive power, because this is defined for this only, this is pi only. If you say we are taking up only two quadrants. Clear? So that is why it is total will be pi. Clear? It won't be 2 pi, because we are not talking about a complete surface, we are talking about a hemisphere. We are talking about a hemisphere which will be pi only. Clear, MATLAB? Why it is pi? Because in all the direction, if you say this is my hand is a hemisphere, it will be having a dome-like structure like this. Fine. So in all the direction will be having the same intensity. So if you integrate this, that means you are adding all this intensity of radiation in all direction. That means we are taking all the radiation in all this direction, which is pi only. So this will be I intensity of radiation into pi will be giving us the black body emissive power. So if you want to calculate what is the emissive power of a non-black body, so you can directly, if you want to have for the non-black body, you can directly write E is equal to emissivity into I into pi. So you can, by using this this equation, you can calculate for any non-black body. Clear? Understood? Because this is the main difficult part which many of the students are not able to understand. The difference between a diffuse body and what is Lambert Cosine Law. Every time seen, like more than 70% of the students are confused between the difference between your E lambda and your intensity of radiation. Many of times they have a confusion like what should be the difference between the monochromatic emissive power and intensity of radiation. Clear? Clear? So this was about the total, we have completed, taken up all the laws of radiation. I hope so you understood. Yesterday we studied about the Stephen-Boltzmann's equation. We have taken up the black body radiation is a strong function of the total emissive power of a black body is a strong function of absolute temperature, which is EB is equal to sigma into T to the power 4, which is Stephen-Boltzmann law, which we have studied in the yesterday's class. Continuing to that, we have studied the 4 different laws of radiation. We have started with the Kirchhoff law. We started with the Kirchhoff law of radiation, where alpha is equal to emissivity. This was our first law. Second was Planck's law. Planck's law basically stated that EB lambda is equal to F function of lambda and absolute temperature. I have given you the example. Next is Wien's displacement law, very important. This is the application of the Planck's law, where we are having your maximum wavelength with the temperature is constant. The multiplication or the product of the maximum wavelength with the absolute temperature will be constant. And the last is Lambert Cosine law, where we first understood what is solid angle and intensity of radiation. After that, we applied this concept onto this body, and we understood there is one law which is Lambert Cosine Law, which is I theta is equal to what is the intensity of radiation at any angle will be equal to the multiplication of from normal to the surface into the cos of the angle between the two radiation. Clear? And after that we understood diffuse surface, because yesterday I told you about the black body. Black body is a perfect absorber, ideal emitter, and a diffuse surface. So diffuse surface, how it is a diffuse surface? I told you because in all the direction will be having same intensity of radiation. If you integrate this, you'll be getting the total black body emissive power, and you can convert for any non-black body if you know the magnitude of this emissivity. Clear? If you know the value of this emissivity, then you can easily get the magnitude of this any non-black body emissive power. Yes, what is your doubt? We need to study mass transfer. No, if you are a mechanical engineer, for a mechanical engineer aspirants, mass transfer is not at all there for UG program. Yes, if you are from a chemical engineering background, then definitely you need to study mass transfer, because for chemical engineering students, mass transfer is also in their curriculum. Fine, but for mechanical it is till we are having only 3 mode of heat transfer, which is heat transfer only. We won't be having any mass transfer, because mass transfer deals with separate analysis, will be having separate dimensionless number, which is not at all there for the mechanical engineering. Clear? So so we have understood what is the different laws of radiation, and like yesterday also I told you about the green card, because those who are serious for their career, they should be attempting the daily quizzes. They should be solving more number of problems. Okay, so this is our green card, which is basically consists of 120 plus mock tests and 24 subject tests, when you can apply your concept. Like if you talk about the today's session, you can solve when you take up the heat transfer topic, you can solve the problems from heat transfer radiation topic. You can attempt this as many number of times if you are taking for the yearly, because this is yearly charges. At present the charge is like 399 only, but after 13th on 13th onwards you'll be the price will be increased. So better why to wait if you are serious about for competitive exam, any competitive exam, take it, it's GATE, ESE, or you are interested in any SSC or RRB JE also. So definitely questions are being regularly asked from these concepts. So if you are good in the concept, but only knowing the concept is not at all important, you should also apply the concept. For applying the concept, you should be having a question bank with you. So for question bank, this is the perfect solution for you, the green card. By using this green card, you can have an access for many number of quizzes. Clear? So it is very important if you are a serious aspirant. So thank you for joining with me. It was a short, crisp session for the different laws of radiation. In the next class, basically I will be talking about the radiation network. We'll be talking about the shielding also. We'll be talking about shielding. We'll be drawing the radiation network, which is very important. Yes, definitely I'll be taking in future. Yes, I'll be taking the session for virtual calculator. Fine, definitely we'll be having session how to use virtual calculator. In upcoming days, definitely we'll be having a session for this. Tomorrow we'll be having a general session by other faculty. Clear? My next class of heat transfer will be on Monday. Fine. On Monday, don't miss Monday's lecture, because Monday is very important. Now we have collected many of the parameters. We have understood various laws. Now it is time to apply those concepts on the practical application, which is the radiation network, because radiation network deals with the practical application of radiation topic. Fine. In this we'll be talking about some of the basic terminologies like radiosity, irradiation, and after that we'll be drawing the network diagrams and different resistance being inculcated in this radiation topic. Clear? So thank you for being with me for this session. And also do like this session, subscribe this channel, prep smart, score better with Gradeup, and always do have, if you are having any doubt, do let me know. You can give your comments and feedback for this session, so that always will be improving for the next upcoming sessions. So all the best for your exams. Thank you once again. So prep smart, score better, go Gradeup, and all the best for your exam. Thank you.